One of the more well-known results of quantum mechanics is the Heisenberg Uncertainty Principle, which states that there is a fundamental physical limit to the precision with which we can simultaneously measure both the position and the momentum of a particle. The less uncertain we are about the position, the more uncertain we must be about the momentum, and the less uncertain we are about the momentum, the more uncertain we must be about the position. This might feel very unintuitive. For instance, why can't we just design ever more precise instruments to make our measurements? Well, it turns out that the Heisenberg Uncertainty Principle is just one special case of a much more general result of uncertainty in quantum mechanics, which in this video we'll refer to as the Quantum Uncertainty Principle, that applies to much more than just position and momentum. In this video, we're going to build up an understanding of the generalized quantum uncertainty principle from a few postulates of quantum mechanics. We won't be deriving the exact mathematical form of this, or of the Heisenberg Uncertainty Principle, but instead getting an intuitive and visual image of how they work. Instead of immediately jumping to position and momentum, let's start by looking at the postulates of quantum mechanics for something simpler that's still affected by the general quantum uncertainty principle, an electron's spin. All of these postulates refer to the observables of a quantum system. An observable is just any number that we can measure from the system, like the position and momentum of a particle, or in this case, the spin of an electron. Specifically, the observable we're currently concerned with is the electron's spin in the z direction. We're actually going to go through these postulates in a different order than they usually show up in. The first postulate states that any observable of a quantum system corresponds to a set of orthogonal basis states, which can be represented as unit vectors which are all perpendicular to each other. The postulate also states that each of these unit vectors corresponds to exactly one possible measured value of the observable. In our case, it turns out that there are only two possible values we can measure for the spin in the z direction, either plus 1/2 or minus 1/2, which we'll just call up and down respectively, and we'll represent them with these symbols. Note that this is a deviation from classical mechanics, where we'd also be able to measure any value between plus 1/2 and minus 1/2, depending on the tilt of the electron. But it's an odd feature of quantum mechanics that we can only measure these two values for the electron. Because there are only two possible measured values, that means we need two perpendicular unit vectors to represent the basis states. Let's use the vector 1, 0 for the up state and the vector 0, 1 for the down state. The direction these unit vectors point in on the Cartesian plane have nothing to do with the direction of spin. They are simply representations of the up and down spin states. Note that if we have more than two measurable values, we need vectors in more than two dimensions. For something like the particle's position, which can be measured as any real number, we need an infinite number of dimensions. The second postulate states that any quantum system is represented uniquely by its quantum state psi, which can be any unit vector, which we can decompose into a sum involving the basis states we previously defined. This is called a superposition of states. In our case, the electron's quantum state can be any of these vectors which lie on the unit circle, as they are all some combination of the up and down states. Note that the basis states themselves are also valid quantum states. The third postulate states that when an observable of a quantum state is measured, the result is random. The probability that we measure a given value is given by the squared absolute value of the coefficient attached to that state. For instance, let's take the state psi equals 0.6 times up plus 0.8 times down. If we have an electron in this state and we try to measure its z-spin, we'll find that it's up with probability 0.6 squared equals 0.36 or 36%, and down with probability 0.8 squared equals 0.64 or 64%. In addition, the third postulate states that the interaction required to measure the system is actually going to cause the quantum state to collapse into the basis state that was just measured. So if our electron was initially in the state above, and we measured it and found an upspin, then its state is now just the up state, and subsequent measurements will have a 1 squared equals 100% probability of getting up again. The same goes if we measure the down state. The z-direction spin isn't the only observable that we can measure. Say we're instead measuring the spin of the electron in the x direction. Again, we'll find that there are only two possible values we can measure, plus 1/2 or minus 1/2, which we can call right spin and left spin, and represent with these symbols. This observable corresponds to a different basis than the z-spin. Intuitively, we'd expect a spin in the x direction to be in between the up and down spins, and indeed, the basis vector for the right spin looks like plus 1 over square root of 2 plus 1 over square root of 2, right in between the up and down states. The basis vector for the left state is instead going to be plus 1 over square root of 2 minus 1 over square root of 2, which is the other state that can be thought of as in between up and down. Any quantum state is also a superposition of these left and right states, but the coefficients, and therefore the probabilities, are different from the ones attached to the up and down states from before. For instance, let's go back to the state we had before. We can re-express this state in terms of the left and right basis states as psi equals 0.7 root 2 times right minus 0.1 root 2 times left. Therefore, if we measure the x spin of this state, then the probability we measure and collapse into the right state is 0.7 root 2 squared, which is 0.98 or 98%, and the probability that we measure and collapse into the left state is 0.1 root 2 squared, which is 0.02 or 2%. Compare this to the probabilities associated with the z-spin, 0.36 and 0.64. The differences in these probabilities is caused by the fact that the basis vectors for our two observables, the z-spin and the x-spin, do not align with each other. It turns out that it is precisely this non-alignment of basis vectors that leads to the quantum uncertainty principle. Let's go back to our vector graph and write down the probabilities of a given state collapsing into the up, down, left, and right states. We'll also visually show these probabilities using the length of these colored bars here. Remember that the possible outcomes of our measurement depend on which observable is being measured. If we measure the z-spin, we can only collapse into the up or down states, and never the left or right states. But if we measure the x-spin, then we can only collapse into the left or right states, but never the up or down states. So these probabilities here are assuming that we are measuring the relevant observable. Watch what happens when we move our state around. Say we have an electron near the up state, like this. Then there is a high probability that when we measure the z-spin, we get the up state, and a low probability that we get the down state. Thus, we might say that the z-spin has low uncertainty. But because of how these states are related to the left and right states, we see that the probabilities of getting those from an x-spin measurement are nearly 50-50. This means that the x-spin has what we might call high uncertainty. The same thing happens for states near the down state. But what if instead our electron is in a state near the right state? Then the x-spin measures as right with low uncertainty, but the z-spin has high uncertainty, as both its states have about equal probability of being measured. The same goes for states near the left state. And remember, if we actually make a measurement, then the state collapses to the measured state. So if we start with this state, where we have low x-spin uncertainty, and measure the z-spin as up, then the state of the electron now changes to the up state, which has no z-spin uncertainty, but maximum x-spin uncertainty, with exactly a 50-50 split in the probabilities. Measuring the x-spin has the opposite effect. So to sum these findings up, if our electron is in a state where the uncertainty of z-spin measurement is low, then the uncertainty of x-spin measurement is necessarily high. And if the uncertainty of x-spin measurement is low, then the uncertainty of z-spin measurement is necessarily high. That's the quantum uncertainty principle. By the way, there's nothing special about these axes. We can measure an electron's spin along any axis, and we'll always get one of two results, corresponding to the two directions along that axis. The relevant basis vectors just get rotated, like this. And the uncertainty principle applies to any pair of observables that have different basis states, because each of these states corresponding to one observable is a superposition of the pair of states corresponding to the other observable. In other words, it is physically impossible for our electron or for our quantum system to have no uncertainty for both observables, because that would require being in two separate quantum states at the same time. Note that none of this is caused by instruments or our methods of measurement. Instead, it's a feature of the basis states themselves and their non-alignment. In general, if the basis states are closer together, then the effect of the uncertainty principle is decreased, but it always applies to some extent unless the basis states exactly match up. Before we go, let's briefly discuss how exactly this applies to position and momentum in the Heisenberg Uncertainty Principle. As we mentioned before, because position and momentum have an infinite number of possible measured values, we would need an infinite number of basis vectors, all perpendicular to each other. This would imply that the vectors themselves must be infinite dimensional. There's a bit of mathematical machinery required to develop the needed theory that we won't fully get into here. But the basic idea is that these particular infinite dimensional vectors can also be represented as continuous complex valued functions in one dimension, which we can graph. The position basis state corresponding to a position x is represented by a function which is 0 everywhere except for a single tall spike at x, while the momentum basis state corresponding to a momentum p is represented by a complex exponential function, which has complementary oscillating sine and cosine waves in the real and imaginary numbers. The momentum determines the spatial frequency, also known as the wave number of these oscillations. Specifically, this wave number is equal to p over the reduced Planck constant h bar, so the larger the momentum, the more rapidly the state oscillates. These position and momentum basis states don't match up with each other, so the quantum uncertainty principle must apply, thus becoming the special case of Heisenberg's uncertainty principle. Thanks for watching. I hope you've learned something cool, and see you next time.